All right, we're going to discuss section 7.8, relationship between conservative forces and potential energy. Okay, we associate potential energy function U for a system with a force acting between the members of a system only if the force is conservative. In general, the internal work done by a conservative force on an object that is a member of the system as the system changes from one configuration to another is the initial value of the potential energy of the system minus the final value of the system, as shown in the equation here. The internal work is equal to U initial minus U final equals the change in delta U, the change in potential energy. The subscript in INT is the internal work to the system, different from WEXT, which is the work done on the system as a whole by an external agent. Imagine a system of particles in which the conservative force F acts between particles, and the configuration of the system changes due to the motion of one particle along the x-axis. Evaluate the internal work done by this force as the particle moves along the x-axis. And we see the work internal is the integral from x initial to x final of fx dx. That's equal to the minus delta U. The f of sub x is equal to the component of f in the direction of the displacement. So we can write this as delta U minus U final minus U initial equals minus the integral from x sub I to xf, initial position to final position of fx dx. Delta U is negative when fx and dx are in the same direction. Example, when an object is lowered in a gravitational field or when a spring pushes an object toward equilibrium. We establish the location of x sub I in one member of the system. It represents our reference configuration. We measure all potential energy differences with respect to this reference x sub I. We define the potential energy function as U sub f, U final of x equals the integral from initial x to final x of fx dx plus U initial, the initial potential energy. It doesn't matter what value we assign to UI because any non-zero value shifts U final by a constant amount and only changes and only the change in potential energy is physically meaningful. In other words, only delta U is meaningful. If the point of application of the force undergoes infinitesimal displacement dx, then we can express the infinitesimal change in potential energy of the system, du, as du equals minus f of x, f sub x dx. The conservative force related to potential energy function through this relationship is as shown. F of x is equal to minus du dx. The x component of the conservative force acting on a member within the system is equal to the negative derivative of the potential energy of the system with respect to x. Okay, let's take a little quiz. What does the slope of the graph of U sub x, U of x versus x represent? The magnitude of the force on the object, I should advance. The magnitude of the force on the object, the negative of the magnitude of the force on the object, or the x component of the force on the object, or lastly, the negative of the x component of the force on the object. And the answer here is D, the negative of the x component of the force on the object. The slope of a ux versus x graph is by definition dux dx. This expression is equal to the negative of the x component of the conservative force acting on an object that is part of the system. This ends our discussion of the relationship between conservative forces and potential energy. Next, we will discuss section 7.9, energy diagrams and equilibrium of a system.